Okay, welcome to 9.3, the end of Chapter 9. We're going to turn our attention now to independent samples for two means. We're going to compare two different populations. So remember that we need to be able to identify when samples are independent, and if they are independent, we'll follow the methods in this section. The only difference with independent t-tests is that there's two different formulas, and that depends on assumptions that we can make about the population variances. For us, that's not going to be a big deal, but when you're working through the text, make sure that, well, I would recommend that you watch this first so that you can see how those two different tests relate. We're going to start with hypothesis tests. The variables and parameters are exactly what you'd expect. Two random variables for the two different populations and two population means. The hypothesis, the null hypothesis, is that there's nothing different between the two populations. They are the same. So we saw that previously in the previous section, and we're seeing that again here. Notice we don't need to form a difference because we will be talking about two different independent populations. Now, as always, our alternative hypothesis is one of three flavors. We could have that the first population mean is less than the second, or simply that they're not the same, or that the first is larger than the second. Any of those could be our alternative hypothesis. The assumptions, there are four of them. We need simple random samples, and we like it when the sizes of each are equal. So not something that we will worry about too much in this class, but that is an issue out there. For us, we're simply going to get sample sizes that are about the same. Remember, there's two usages of the word independent. And in this second case, the two samples are independent. Basically is ensuring that we are not surveying or measuring the same members of two different populations, that they're independent in the sense that they don't overlap. And of course, we need to show that we have normally distributed populations. So the way that we can get that is either because the sample size is greater than or equal to 30, or because the populations are known to be normally distributed to begin with. Now, this is new, and this is a word that will follow us throughout 9.3, and that is pooling. So if the population variances, now we say variances in 9.3. We didn't say variances before. We say variances now because we are going to use the variances in the test to see if we have to pool or not. That's not going to be an issue for us, as I've said before, so pooling becomes an issue. So if the population variances are known to be equal, then we can pool the sample standard deviations. Otherwise, we do not pool the sample standard deviations. And if you're looking at that thinking to yourself, how often are we going to know the population variances, let alone the fact that they're equal? And you're right, that does not happen very often. So more often than not, in this last assumption that we're making, we're going to not pool. So the sample statistic, the test statistic, and the degrees of freedom, remember these are t-tests because of what we were just talking about, the standard deviations. The t-test comes to us in a formula. The p-value is based on the alternative hypothesis. So it's either a left, right, or two-tailed test, and that depends on what it is that we are testing. And I don't know if I've said this recently or if I've said this in the videos, but it's useful to remind yourself that the p-value is a probability. It's the probability of getting results as extreme as the sample while assuming the null hypothesis. Part of the power of hypothesis testing is that we can assume what we're trying to show isn't true. We can assume the given information in the null hypothesis and say, well, if that's true, what would the probability be of getting the results that we did in the sample? As extreme means that we're taking into consideration which side of the normal curve we're looking at, the right tail, left tail, or both. And then the conclusion, this is copied and pasted as always, so there's a reminder that nothing new's here. If the p-value is less than alpha, we reject the null hypothesis. Otherwise, there is not enough evidence to support the alternative hypothesis. And the interpretation, that's where we say as clearly as possible in clear English what that means. Okay, so let's look at an example. It says that the cholesterol level of patients who had heart attacks was measured 2 days after the heart attack. The researchers wanted to see if patients who have heart attacks have higher cholesterol levels than healthy people. So they also measured the cholesterol level of healthy adults who show no signs of heart disease. Does the data show that people who have had heart attacks have higher cholesterol levels over patients that have not had heart attacks? Test at the 1% level. In fact, the healthy individual data may be entirely new unless you've been working through the examples in the text, in which case you've already got the cholesterol level data for healthy individuals. But compared with the data that we used in 9.2, you'll need to add 2 new cholesterol level for heart attack patients. That's the 228 and the 235. Just put that new data in. Okay, we're on the next page and we're working through the hypothesis test itself. The first thing is the random variables and the parameters. So the first thing I see is the cholesterol level of a heart attack patient. So that's going to be our random variable x sub 1. X sub 2 is the cholesterol level of healthy individuals. We're doing a t-test. We're talking about population means. So our parameters, remember parameters come from populations, is mu sub 1, the mean cholesterol level of all heart attack patients, and mu sub 2, the mean cholesterol level of all healthy individuals. Our hypothesis test, well, the null hypothesis is exactly what you'd expect. That is, there's nothing to see. The two populations have the exact same mean, or at least within the level of statistical significance. The alternative hypothesis is what we were asked to test. We were asked to test the claim that that first population, mu sub 1, that's the population of folks who've suffered a heart attack, their cholesterol level is greater than those folks who didn't show any sign of heart disease. And a reminder of alpha, our level of significance. Alpha is 1%, 0.01. Our assumptions, and you may be kind of feeling uncomfortable at this point because nothing about this said that those samples were random. And so we say that. Perhaps this is a unique set of samples. We don't know. The next thing that we need to say is that new usage of the word independent, and that comes to us from the fact that these are in fact different populations. In other words, you either have no sign of suffering from heart disease or you've had a heart attack. We also need to say something about being normally distributed. And just like before, we're going to say that cholesterol levels are known to be normally distributed. So that works out nicely for us. And last but not least, we have to make sure that we're doing the correct test, that we're actually doing what we're supposed to be doing. So we're doing this test. We're saying that, honestly, we don't know anything about the population standard deviations. You can say that in exactly the same way by saying we don't know anything about the population variance. And because of that, we will not pool. So we've got 2 independent sets of data. So let's go to our GeoGebra application. So these are for the healthy and the patients who've had heart attacks. Let's select that data. Let's open a GeoGebra spreadsheet. So we'll go into View, turn on Spreadsheets, turn off Graphic and Algebra, and let's paste that data in. Looks like it got all 30 of the first column and 32 of the second. So now we're going to select both, and we're going to ask for a multiple variable analysis. We've got some stacked box plots, which is somewhat interesting. We can certainly see that among the second population, the cholesterol levels are lower, with looks like an outlier out there. Let's get our statistics, And let's give that some room. It told us the sample statistics. That is the mean of the two samples. That first sample were folks who'd suffered heart attacks, and the second sample is healthy individuals. And notice that the sample means do differ. Now, without knowing the standard deviation, it's difficult to know how significant that is. And let's do a t-test difference of means. I'm going to give that some room again. We're not going to pool it. And let's take a look again at the data. Remember that left column, the data that ended up in column A, is for the heart attack patient. So that's the average of that would be mu sub 1. And then the healthy individuals, that's the second column B. The average of that would be mu sub 2. So when we look at this, we're now asked for the alternative hypothesis. Remember that the first population were the heart attack. It says, does the data show that people who've had heart attacks have higher cholesterol levels over patients who have not had heart attacks? So we're basically asking if this first set of data in column A is greater in the average to the second. So when we're choosing this, that means that that difference, if mu sub 1 is greater than mu sub 2, then we expect it to be positive. So that is greater than 0. Here's our p-value, our t-values, and then information for each of those two samples. So there's our t-value, and there's our p-value. So the conclusion, well, that p-value is much smaller than alpha, so we are going to reject the null hypothesis. And we can say that nicely. There is sufficient evidence to say that healthy individuals have lower cholesterol levels than heart attack patients. Now that's all very well and good, but you might ask yourself, how much less? What is the difference in the cholesterol levels? And to do that, we'll answer that question with a confidence interval. Steps 1 and 3 are the same as what we saw before, so then we start with step 3, the new step 3. Our confidence interval, this is just copied and pasted from before. It's our point estimate plus or minus the margin of error. And our point estimate, well, the thing that we know about, two sample means. So we're simply going to say what the difference in the sample means is. Now the margin of error comes from multiplying our t-score by that standard error there. And that comes from either using Bell or some sophisticated tables that are also out there. And either of those will work. So the confidence interval, and this is just restating what we've said before, we're making claims about the difference in the population means by how much one is bigger or smaller than the other. So we're simply going to take that point estimate, the difference in the sample means. We're going to subtract the margin of error to get our left endpoint. That's going to bound our population mean difference, and then we'll add the error to get our right endpoint. And of course, that E comes from T, and T is the bridge between our confidence level and the margin of error. So T is the thing that connects C to E. It says to use the data that we did previously. It says find a 90% confidence interval for the mean difference in cholesterol levels between heart attack patients and healthy individuals. Okay, so let's actually perform a hypothesis test. Steps 1 and 3 are the same. They become steps 1 and 2. The new step 3 is to state our sample statistics and the confidence interval. So here's our sample means. Our next question is to create a confidence interval for the difference of means. So let's go back to our test and let's change it to an estimate for the difference of means. Let's give ourselves some room there, and let's go back and check what the confidence level was. So it says 99%, so we can change that confidence level to 0.99. And now we have our lower limit and our upper limit for our confidence interval. And here is our confidence interval. And of course, our confidence level is 99%. The statistical interpretation is when we say that there is a 99% chance that that interval between 30.064 milligrams per deciliter and 82.24 milligrams per deciliter contains the true difference in population means. Now, look at this in clearer English, and it's actually pretty interesting. The average cholesterol level of a heart attack patient is between 30 milligrams per deciliter and 82 milligrams per deciliter, more than the average cholesterol level of a healthy individual. Now, in the book, there's a lot of discussion as part of the hypothesis test and the confidence interval about when to pool and when not to pool. So what I've done is a little bit different. I've moved all of that discussion to this last page of our workbook and talk about it in one place. I'm going to say right at the beginning that you can get reasonably good answers by always saying no to your calculator when it asks to pool or not. But let's talk about this just so that the rest of that discussion in the book makes a little sense. First off, we are assuming that the two population variances are not equal. That's what's allowing us to say that we should not pool those results. And so you might say to yourself, well, what would happen if the population variances were equal? And the advantage there is that there's a simpler method of finding the t-score and the margin of error. The problem, of course, is we don't know the population variances. We only know the sample variance and not the population variance. So if we want to use the simpler method, we first have to show that the population variances are equal. And there's a way to do this. No great surprise. And it is a brand new test. It's an F test. So to do that, we have to show that the variances are equal. That means that the ratio of the sample variances is not unusual. So to do that, we have to ask this question, and that is if the probability that the F score is greater than the ratio of the variances, and if that probability is greater than or equal to 5%. I've stated this two different ways because the larger of the two variances has to be in the numerator. So the larger of the two has to be upstairs. So that allows us to use a simpler formula. And beginning on page 324 in our text, she shows you how to use that simpler formula. And here they are. So here are the t hypothesis test and the error for the confidence interval. And you'd have to agree that those are a little bit simpler. Now I should say right now that you do not need to use these simpler tests. In practical terms, the only difference is a slight change in the p-value. That said, we're now going to work through an example where we do perform an F-test to check to see if we can pool the sample means. To do that, I've copied the data, 2 columns for the beef and the poultry hot dogs. Let's go into a GeoGebra spreadsheet and paste that data in. It looks like we got all 20 of each. We're now going to determine whether the data is normally distributed, and to do that we need to look at each set separately. So let's do one variable analysis on column A. Here's a histogram. It certainly looks skewed to the right, doesn't look symmetric, but we'll now check a box plot. We're checking for outliers. It looks like it would show us an outlier if there was one. There are no outliers. Let's now look at the normal quantile plot, and the data looks very closely aligned along the line. So the first set of data, I think that was the beef hot dogs, looks like it is perhaps normally distributed. Now let's look at the poultry hot dogs, the second set. Again, let's do one variable analysis on it. Let's look at a histogram, and that certainly looks curious. not bell-shaped in the least. There's a big gap in the middle. It looks like randomly distributed peaks compared to a normal distribution. Now let's look at a box plot. No outliers, and then the normal quantile plot, and the data is spread around pretty far from that line. So it looks to us like we can conclude that the second set of data may not be normally distributed. So we remind ourselves that a t-test for a difference of means is fairly robust, but that our results may not be accurate. Okay, now let's do two-variable analysis. Let's look at columns A and B, and let's see what we have. And now what we're going to do is determine whether we have to not pool or whether we're allowed to pool our data when we go into the difference of means. So just as a kind of preview, when we do that, we're going to be asked whether we can pool that data. So I'm going to copy the standard deviations for the samples, that is the S for this first column. Remember the sample was 20 for that, and I'm going to go into the F cumulative distribution function. So our first sample had a size of 20, and let's plug in the standard deviation. Oh, that's a lot of decimal accuracy there. And let's, my goodness, that's a humongous amount. Something went kind of wonky there, so let's go back in and copy that again and see if we got it this time. Looks like we got it this time. So there is our standard deviation. We need to make that into variance by squaring it, so we'll do that. Now let's remind ourselves that the second sample also had size 20, so we'll put that in. Let's get its standard deviation. Let's plug it in. Let's see if that worked. It looks good, 81.17856. We need to square that to get variance, and it looks like our F value is approximately 16%. Let's go back to the workbook, and we can remind ourselves that what we're looking for is whether the probability that that F test is at least as strong as 5%, that is greater than 5%. And it looks like we've got about 16%, and that means that we can use the simpler test. That means that we can pool the sample means. So when we go back to that t-test, we can pool those sample means. Now, before you look at the p-values and the t-values, let's remind ourselves that this is a test, a hypothesis test. We've got the null hypothesis, but we also need the alternative hypothesis. So let's go back to the text itself. And it's, well, actually, before we do that, let's remind ourselves of the means here. So it looks like for the first sample, the mean was 401. For the second sample, the mean was 450. So it certainly looks to me like there's less sodium in the first sample than the second. So let's see if that agrees with what our text is asking. Is there sufficient evidence to show that beef hot dogs have less sodium on average than poultry hot dogs? So here's beef in the first, and it's asking that us to check a hypothesis test whether that's actually less than the amount of sodium in the poultry hot dogs. So first column, less than second column. Let's see what that means here. So the first sample less than the second sample. So mu1 is less than mu2. That is, the first mean is less than the second mean. So when you subtract a larger number from a smaller number, you get a negative. A negative number is less than 0. So let's make sure we've got that correct. And now we've got our p-value, our t-value, and of course our degrees of freedom. We've selected pooled. Now, just as a point of interest, notice that if I disselect pooled, the p-value only changes by a very, very slight amount. Let me do that again. And you can see that it's in the, tenths, hundredths, thousandths, 10,000ths place that difference occurs. The degrees of freedom also changing. Let's leave that pooled. That's why we did the F test. Now our p-value is 0.05075. Boy, just a tiny bit more than 5%. Let's see what that means for our question. So let's go back to the text. And it says check at a 5% level of significance. Well, we're pretty darn close there. So let's remind ourselves that when the p-value is greater than alpha, we're going to fail to reject the null hypothesis. There is not enough evidence to show that beef hot dogs have less sodium than poultry hot dogs. And remember, we were not convinced that the data was normally distributed. So we do realize that many of the assumptions are not valid, so this interpretation may also be invalid. A quick reminder, we copied the data into GeoGebra. We looked at the data separately to see if it looked like it was normally distributed. The second set of data certainly did not. We then did an F-test using the standard deviations given to us when we did the t-test with the difference of means. We had to square those to get variances. That gave us a p-value of 15%. 15%, well, actually closer to 16. That's more than 5%, so we were allowed to pool those. We then noticed that both the data and the question asked us whether mu sub 1 is less than mu sub 2. We wrote that as the difference. And then we got our p-value, we compared it to alpha, and we made our conclusion.